So far we've looked at phase transitions from a macroscopic phenomenological perspective. We derived general coexistence conditions, we derived the Gibbs phase rule. Today, for the first time, we're going to look at a simple microscopic model that gives rise to a phase transition. This microscopic model is the model of a ferromagnet. It's the Ising ferromagnet. On this page, I describe a little bit the setup of the model. There's a lot of text. That's why I prepared the slide beforehand, so we don't lose too much time just writing text. The Ising ferromagnet is a very simplified model of a ferromagnetic solid with a strong anisotropy. So there's a preferred direction in space, and the solid exhibits magnetization only along this preferred direction, along this preferred axis. And we can choose our coordinate system such that the z-axis of our coordinate system coincides with this preferred axis. Very similar to the model of a paramagnet that we had looked at, we consider spin 1/2 with an associated magnetic moment on a lattice, on a fixed crystal lattice. There are n sites, so n spins in total at sites from 1 to n. And as before, as in the case of the paramagnet, we have a Pauli spin operator. And since we have only this preferred direction, we always mean the Pauli spin operator along the z-axis. So we don't write this explicitly. We just denote it by sigma I. That's the Pauli matrix or spin operator along the z-axis for site I, for spin I. And then we apply an external magnetic field. Also, that external field is always understood to be along the z-axis, and it has magnitude B. Now, the Hamiltonian consists of two parts. The first part looks just like the Hamiltonian of the paramagnet. It's the interaction of the spins with the external magnetic field. That's the first term. But what's new is that we now introduce an interaction between the spins. And this is the second contribution to the Hamiltonian. You sum over all pairs of spins, sum over I and j, and then there's some coupling constant which is not specified, Vij, that describes the coupling strength between spin I and spin j. And then there's the Pauli spin operator for spin I and the operator for spin j. So it's the Hamiltonian of the paramagnet with an added interaction, pairwise interaction between the spins. In equilibrium, this Ising ferromagnet attains canonical state, which has the standard form, 1 over partition function e to the minus beta times Hamiltonian. And the Hamiltonian depends on this external control parameter B. The external field is a control parameter. So the equilibrium state and also the partition function depend on inverse temperature, which is a Lagrange parameter, and B as a control parameter. And we would like to find out something about this equilibrium state. And the objective is to show that there are circumstances under which there's a phase transition. And more specifically, there is a phase where the ferromagnet exhibits no spontaneous magnetization, and then there's a regime where the ferromagnet exhibits spontaneous non-zero magnetization. And the transition from one regime to the other turns out to be a phase transition. Now, it's very difficult to calculate exactly this equilibrium state due to this quadratic interaction term in the Hamiltonian. So that makes it difficult to evaluate this exponential. And therefore, one resorts to an approximation. That's the so-called mean field approximation. One approximates states with the so-called mean field approximation. And the mean field state has the following form. A mean field state is characterized by a parameter lambda, and it has this characteristic Gibbs form with lambda as a Lagrange parameter and the relevant observable being the sum over all Pauli spins, where the lambda is still unknown, so it is yet to be determined. This looks like the equilibrium state of a paramagnet with up to some constant of proportionality, lambda being the external field, the magnetic field. This is why the lambda, as I said, up to constant prefactors, the lambda is called the mean field. But now it's not just the external magnetic field, but it includes the field generated by the totality of all spins. So I have this ferromagnet with many spins, and say a majority of spins points in a certain direction, and then the net effect is that I have a magnetic field generated by the spins themselves. Now, when I look at an individual spin, then this individual spin feels not just the external magnetic field that I apply, but it also feels the magnetic field generated by all the other spins. And so the lambda is the mean field, and it includes the field generated by the totality of spins. If we don't apply any external field, then the lambda represents only this mean field generated by the totality of spins. So by introducing this form of the density matrix, we simplify the problem a lot, because the most general density matrix has a huge dimensionality. We have n spins. Each spin lives in a two-dimensional Hilbert space. So the n spins live in a 2 to the power n dimensional Hilbert space. So a general density matrix in this huge Hilbert space has a huge number of parameters. And now we restrict our attention to a special class of density matrices, which are characterized by a single parameter only, namely by this lambda. And now we would like to find the equilibrium state amongst this, in this very restricted class of states. So the objective is to find the equilibrium state within this restricted class of mean field states. I'm not going to discuss here the limits of validity of this mean field approximation. That's beyond the scope of today's lecture. So how can we determine the equilibrium value for lambda? How can we find, in this class of mean field states, how can we find the equilibrium state? We have a system at a given temperature. We consider this Ising ferromagnet at a given temperature T. What do we do if we seek equilibrium at a given temperature? We use the free energy and we seek the minimum of the free energy. Free energy now considered as a function of lambda. So we should consider the free energy. The free energy depends on temperature and external magnetic field. These are the two variables that I control externally. The ferromagnet is in contact with the heat reservoir, so I control the temperature. It's subject to the external field, magnetic field B. These are the two variables that I control from the outside. And then I can assign a free energy to any state rho from this class of mean field states. So not necessarily the equilibrium state. The equilibrium state will be that state that minimizes the free energy, but the free energy is just as well defined for arbitrary states. And that's what we had discussed. By definition, the free energy for an arbitrary state is its internal energy, which is the expectation value of the Hamiltonian in that state, minus the temperature controlled from the outside by the bath, by the reservoir, times the entropy of that state. Let's look at the various terms that appear in the formula for the free energy. Let's start with the expectation value of the Hamiltonian. The Hamiltonian had the form Bohr magneton, external magnetic field, and then the sum over I, Pauli operator sigma I, and now we are taking the expectation value, so we have the expectation value of sigma I in the state rho of lambda. And then we have the interaction term. It was minus 1/2 sum over pairs of spins, I and j, coupling Vij, and then we have sigma I, sigma j, and now we are taking the expectation value, so we have sigma I, sigma j, expectation value in rho of lambda. Now already from our treatment of the paramagnetic salt, we know what the expectation value of sigma is in such a state rho of lambda, because the equilibrium state of a paramagnet had precisely the same form as our mean field states. So we can simply take over the result that we had obtained for the paramagnetic salt for the expectation value of sigma. And we find that this is, the prefactor remains, and then we have all the sigma i's have the same expectation value, regardless of location. The expectation value is minus the hyperbolic tangents of lambda, and since we sum over all I, we get a number of spins as an extra factor, the number n of spins. So this is comes from the discussion of the paramagnetic salt. Let's next consider this expectation value of this product, sigma I, sigma j, of spin operators. Now, the mean field statistical operator does not contain any correlations. It factorizes. It has, in the exponent, it has lambda times the sum of all I, sigma I. And so you can also write that as a tensor product of e to the minus lambda sigma I, and then tensor product over all I of such exponentials. So you have a tensor product of independent spins, and there are no correlations in that state. This means that this expectation value of this product of sigma I and sigma j is simply equal to the product of expectation values. Yeah? So this is, as I said, this is because rho of lambda factorizes, and hence there are no correlations. This implies that the expectation value simply factorizes. Now, as in the case of the paramagnetic salt, as we had discussed for the first term, each of these two expectation values is minus the hyperbolic tangents of lambda. So the product of these two is simply equal to the square of the hyperbolic tangents of lambda. In particular, this is independent of I and j, and this means that this sum here over pairs of spins really applies only to the coupling constants, Vij. And we can define this as 1/2 times the number of spins times a little v. This is roughly a measure for the average coupling strength between spins. Next, let us look at the entropy that features in the formula for the free energy. The entropy of such a mean field state, this is by our general framework, this is k times the log of the partition function of lambda plus k times Lagrange parameter lambda times expectation value of the associated observable. This is here the sum over I sigma I in the state rho of lambda. Once again, we can take over here the results from the discussion of the paramagnetic salt and find that this is equal to k times the number of spins, the log of the hyperbolic cosine of lambda, plus k times the number of spins times log 2. This comes from the log of the partition function, and then from the expectation value times Lagrange parameter, we have minus k lambda n times the hyperbolic tangents of lambda. So this we take over again from the paramagnetic salt. Together, this gives the formula for the free energy of such a mean field state at temperature T and external magnetic field B. It is minus Bohr magneton, external field, number of spins, hyperbolic tangents of lambda, minus 1/2 NV hyperbolic tangents squared of lambda plus KT lambda n hyperbolic tangents of lambda minus KT n log of the hyperbolic cosine of lambda minus KT n log 2. So it's a rather lengthy formula, but you can write it down in the mean field approximation. You can write down a correct, precise analytical expression for the free energy of an arbitrary mean field state, not necessarily the equilibrium state. But now we seek equilibrium. And this corresponds to a minimum of free energy. And at a minimum, the derivative of the free energy with respect to lambda must vanish. And when you do that with this lengthy expression, you find the condition that the hyperbolic tangents of the equilibrium value of lambda must be equal to kt over this coupling parameter little v times the equilibrium value of lambda minus Bohr magneton external field over v. This is the equilibrium condition for the ferromagnet, the Ising ferromagnet, in the mean field approximation. Let's now see how this result explains and gives rise to a phase transition. And for simplicity, let us focus on the case in which we have no external magnetic field. We restrict ourselves to the case B equal to 0, no external magnetic field. In this case, the equilibrium condition simply reads kt over v, I just flip sides here, kt over v times the equilibrium value of lambda must equal the hyperbolic tangents of lambda. Let us sketch the left and the right-hand sides as functions of lambda. So we have lambda, and let me indicate +1 and -1. The hyperbolic tangents of lambda has this shape. This is the blue curve is the hyperbolic tangents as a function of lambda. Now the left-hand side is just a linear function, it's a straight line with the slope kt over v. And now there are two cases. There's the case where the slope, where kt over v is larger than 1. In this case, it looks like that. Yeah? So this is the left-hand side. In the case 1, where the slope kt over v is larger than 1. If, on the other hand, the slope kt over v is smaller than 1, the hyperbolic tangents at lambda equal to 0 has slope 1. So if the kt over v is smaller than 1, then the straight line will have this shape and will intersect the hyperbolic tangents. This is the case number 2, where the slope kt over v is smaller than 1. Now, if kt, in the first case, if the slope is larger than 1, kt over v is larger than 1, then this equilibrium condition can be satisfied in one point only, for one value of lambda only, namely at lambda equal to 0. If, on the other hand, the slope is smaller than 1, case number 2, then there are two more values for lambda where the equilibrium condition is satisfied, namely this point here and that point there. Let me call this lambda plus and lambda minus. And due to symmetry, this is simply minus lambda plus. So we find that there are two cases. Case 1, this is where I can now solve the condition for T, and I can say this is where the temperature is larger than V over K, and let me define this as Tc, a critical temperature. When the temperature is larger than this critical temperature, then there is a single solution, namely lambda equilibrium is equal to 0, and this corresponds to no magnetization. In the second case, where the temperature is smaller than this critical temperature, we have two additional solutions, lambda plus and lambda minus. And now what you still have to do is to check now which of these three solutions really gives the lowest free energy, because that will be the equilibrium. We have three candidates, 3 points at which the derivative of the free energy with respect to lambda vanishes. So you have 3 local extrema, but you still have to find out which of these is actually the minimum and where the equilibrium lies. And it turns out that at lambda plus and lambda minus, the free energy is strictly smaller than the free energy at lambda equal to 0. So actually lambda plus and lambda minus correspond to the equilibrium. Yeah? So these two additional solutions, lambda plus and lambda minus, give a lower free energy than lambda equal to 0. And therefore, now a non-zero lambda corresponds to a non-zero magnetization, and therefore in this regime, in equilibrium, you have a non-zero magnetization. Now both lambda plus and lambda minus, due to the symmetry of the problem, give the same value for the free energy, so they are both possible equilibrium states, and then this is just a matter of chance, of accident, whether the magnetization will be in the plus direction or in the minus direction. So you have spontaneous magnetization in one of these two directions. You should check, I think that's a good exercise, if you verify for yourself. I'm not going to do this calculation here, but you should check that indeed the free energy, which is a function of temperature, and here I omit B because we said no external magnetic field. So as a function of T and rho at lambda plus or minus is indeed strictly smaller than the free energy at lambda equal to 0. So this is how you find a phase transition. You have here a critical temperature Tc. Below this critical temperature you have spontaneous magnetization, and above critical temperature this spontaneous magnetization vanishes. These are the two phases. Let's have a closer look at the behavior of this spontaneous magnetization, in particular near the transition temperature, near the critical temperature. And what we still have to find out, what we still have to determine, is the order of this phase transition. So the only result that we have found so far is that we have some phase transition at this critical temperature Tc, which is V over K, and it's a transition from a phase which is not magnetized to a phase where we have spontaneous magnetization. Now the magnitude of this spontaneous magnetization is up to a prefactor minus the expectation value of the Pauli spin operator. We had discussed that already for the paramagnetic salt. If you want to relate now this little m to the physical magnetization, you just have to multiply it by some constant factor. But it's essentially the minus the expectation value of sigma, of the spin. Of this we know that it's the hyperbolic tangents of lambda. And now in equilibrium, in this magnetized phase, lambda is one of these two values, lambda plus or lambda minus, and correspondingly we also have m plus or m minus. We can look at two limiting regimes. One is that the temperature goes to absolute zero, and the other is that the temperature approaches the critical temperature, so we are nearing the phase transition. In the first case, the temperature goes to zero. Then when you look at the solutions of the equilibrium condition, you can also see that very easily graphically. You think of where these two curves intersect. As the temperature goes to zero, the slope of this straight line approaches zero, and the two intersection points move to plus and minus infinity. So in this limit, lambda plus or minus approach plus or minus infinity, and the hyperbolic tangents of that, so the m plus or minus, approaches plus or minus 1. And this means that in this regime near absolute zero, the spins are perfectly ordered. They are either all spin up or all spin down. Next, let us look at the case that we approach the phase transition. So we are just below the critical temperature, just below Tc. Well, then the lambda plus and minus become very small. They approach zero. And this, when the lambdas are slow, when the lambdas are small, then I can Taylor expand their hyperbolic tangents. So then it is allowed to expand the hyperbolic tangents of lambda, and I just take the first two terms, namely lambda minus 1/3 lambda cubed. So these are the two lowest order terms in the Taylor expansion, and I can do that for small lambdas. Then the equilibrium condition, the linear function, we can also write in the form T over Tc times lambda. And the hyperbolic tangents on the right-hand side, we can approximate by its Taylor expansion for small lambda. So we replace that by lambda minus 1/3 lambda cubed. In this approximation, we can solve for lambda. We get an analytical result for lambda. We find that lambda plus or minus is then plus or minus the square root of 3 times the square root of 1 minus T over critical temperature. And this is, again, for small lambda, the hyperbolic tangent is up to this cubic correction, but if you say even this is small, then this is the hyperbolic tangent is approximately linear near lambda equal to 0. So this is approximately then equal to the magnetization m plus or minus. And so if we plot the magnetization, and let's consider the positive case m plus as a function of temperature, and somewhere here is the critical temperature. We know that above the critical temperature the magnetization is 0, and just below the critical temperature we have this characteristic behavior. It goes like the square root of 1 minus t over t critical. And the shape looks roughly like that. Yeah, and then it continues somehow for lower temperatures. And this blue curve at the critical temperature has a divergent derivative. So at Tc, the response coefficient, partial m plus over partial over temperature. So this describes how the magnetization changes when I vary the temperature. And this response coefficient at the critical temperature diverges. Now the magnetization is a thermodynamic variable that you can obtain from the thermodynamic potential, in this case the free energy, by taking the derivative with respect to magnetic field. So the m plus, the magnetization, is up to a prefactor a first derivative of the thermodynamic potential, in this case the free energy. So the response coefficient, the derivative of the magnetization with respect to temperature, this is therefore a second order derivative of the potential. And now when you look at this curve, you see that the magnetization itself is a continuous function. We consider magnetization as a function of temperature. It's a continuous function. There are no jumps, no divergences. So it's not a first order phase transition. But the response coefficient, which is the second order derivative of the potential, the response coefficient diverges at the critical temperature. And now according to the Ehrenfest classification, this means that this is a second order phase transition, because we have a discontinuity, we have a divergence occurring for the first time in a second order derivative of the thermodynamic potential. To conclude the chapter on phase transitions, I would like to give you just a qualitative outlook on the so-called Landau model for phase transitions. I just want to show you the basic idea with the help of a few figures, a few graphs. If you remember the Ising ferromagnet that we just discussed, then, and you consider first the case in which we are above the critical temperature. What we had done was that we had restricted our attention to a specific class of states, namely these mean field states. And these mean field states were characterized by a parameter, by the parameter lambda. This is an example for a so-called order parameter. So quite generally, if we go beyond the Ising ferromagnet example, you can you can parameterize states with one or a few so-called order parameters. And here we had the lambda, or equivalently, and perhaps even better, we could also use the M, the magnetization that is associated with the lambda. It's just related by this hyperbolic tangent. Then, as a function of this parameter, we looked at the behavior of the appropriate thermodynamic potential. So we have, to formulate it more generally, we have an appropriate potential. Here, in our case, that was the free energy. And then we looked at the behavior of this potential as a function of our order parameter. In the first case, where the temperature was above the critical temperature, the potential, here the free energy, had a single minimum only, and that was at lambda equal to 0, or m equal to 0. So the potential as a function of the order parameter qualitatively had this shape, with a minimum at the order parameter being 0. Yeah, so the equilibrium here was at the order parameter being equal to 0. When we go below the critical temperature and we look again at the potential as a function of the order parameter, then we found that suddenly we have new minima at values for the order parameter different from 0. We still had a local extremum at the order parameter at lambda being equal to 0, but this was no longer the minimum. Rather, we had the minima at the lambda plus or minus, which were different from 0. So the shape of the potential as a function of order parameter is now as follows, qualitatively. And the minima are now situated here. So then we find that the equilibria are at order parameter different from 0. Let me squeeze in the case where the temperature is just below the critical temperature, to see how this evolves as I lower the temperature. And then the equilibria are different from 0, but very close to 0. And then as I lower the temperature further, they move further away from lambda, or from order parameter being equal to 0. What I drew here, this is characteristic for a second order phase transition. You can draw similar graphs also for first order phase transition. The difference is that as you fall below the critical temperature, the new minima will be immediately further away from 0. So it's not here in the case of a second order phase transition, as you go below the critical temperature, just below the critical temperature, the minima are practically still at 0, and then gradually they are moving away from the order parameter being equal to 0. If you have a first order phase transition, then as you go below the critical temperature, immediately the minima will be a finite distance away from order parameter equal to 0. Yeah, so what I drew here, that was the scenario of a second order phase transition.